In this video, we will be looking at logarithmic functions, so logarithms. A logarithmic function with base a is defined as y equals, we read this as log base a of x, if and only if x is equal to a raised to the y power. This is going to be very, very powerful. We are going to restrict it to where x must be greater than 0, a must be greater than 0, and a cannot be equal to 1. So a being greater than 0 and not being equal to 1 follows from when we were doing exponentials. We said that the base has to be positive and it can't be equal to 1. I know when we graphed exponentials that we couldn't get out 0 or a negative number, so that's where this x being greater than 0 is going to come out. What I need to point out here is that the two equations, y equals log base a of x and x equals a to the y power, mean the exact same thing. They are conveying the same information. All right. One way my students try to remember how to go back and forth between these, I'm going to switch the equations to be written the other way around. So we have log base a of x is equal to y, and a to the y equals x. A lot of students have told me to think like a snail. So if we have log base a of x equals y, we start at the a and snail around. We get a to the y power equals x. And then if we have the exponential part, we can still think snail. Log base a of x equals y. So it's giving you the order that things go in. Just keep in mind that if you use the snail idea, then your log has to be on the left and your exponential has to be on the left. But it's a good way to remember it if that works for you. If not, just practice. We are going to go back and forth between these two forms a lot. So make sure you're getting figured out what goes where. So what this is saying is that an exponential function means the same thing as a logarithmic function. They are conveying the same information. All right, so we can think of a logarithm as an exponent. For example, if I want to figure out what log base 4 of 64 is, then I could say 4 raised to what power is 64? Well, log base 4 of 64 is equal to 3 because 4 raised to the third power equals 64. That's what we're going to be practicing a bit in the beginning of this section. We're going to evaluate a few logarithms. First up, we want log base 4 of 2. If I say this is equal to x, then I would have 4 raised to the x power is equal to 2. Well, that doesn't really help, does it? Wait a minute. I know that the square root of 4 is equal to 2. And we practiced rational exponents earlier. This is 4 to the first power. But because it's the square root, I'm going to have 2 in the denominator. So 4 raised to the 1/2 power is equal to 2. That means my exponent is 1/2. X is equal to 1/2. So 4 raised to the 1/2 power is equal to 2. That conveys the same information as log base 4 of 2 equals 1/2. We want to figure out what log base 2 of 32 is. We can say it equals x. And if I put it in exponential form, we'd have 2 raised to the x power is equal to 32. So what power do I have to raise 2 to get 32? Well, 2, 4, 8, 16, 32. X has to be equal to 5. So if I replace the x with 5, we get that log base 2 of 32 is equal to 5, because 2 to the 5th power equals 32. Log base 3 of 1, if I say it's equal to x, put it in exponential form, 3 to the x power is equal to 1. What power do I have to raise 3 to get 1? Well, anything except for 0. Raised to the 0 power is 1. So I want to raise this to the 0 power. So that means log base 3 of 1 is equal to 0. Finally, we're looking at log base 3 of 1/27. I'll call it x for now. So 3 raised to the x power is equal to 1/27. Well, I know that 3 cubed is 27, but I don't want that 27 in the numerator. I want it in the denominator. So to move it to the denominator, I can make that exponent negative. So 3 to the negative third power is 1/27. I want my exponent, x, to be a negative 3. So we get log base 3 of 1/27 is equal to a negative 3. We are going to practice this a lot, going back and forth between our different forms. Exponential and logarithmic functions are inverse functions. They undo each other. And that's one reason we're allowed to do this back and forth idea. Logarithmic equations can be written as exponential equations, and exponential equations can be written as logarithmic equations. So here we have some logarithmic equations. We just want to rewrite them in exponential form. So first up, we have log base 3 of 9 equals 2. If I use that snail idea, I'll have 3, 2, 9. So 3 to the second power equals 9. These statements are always going to be true, so that'll be nice that you can kind of check your answers, because 3 squared is equal to 9. If we have log base 5 of 25 equals 2, I'll have 5 squared equals 25. Then if I have log base 10 of 0.01 equals negative 2, I'll have 10 to the negative 2 power equals 0.01. So that's going that direction. We're going to see if we can go the other direction. If we start with the exponential, see if we can get back to a logarithm. So we'll have 2 to the third power equals 8. I can do the same snail because my exponential's on the left. I just have to start with log, and then I get base 2 of 8 is equal to 3. That's just how that's going to work. Looking at the next one, we'll have log base 5 of 25 is equal to 2. Next up, we'll have log base 10 of 1/10,000th is equal to negative 4. And then we'll have log base 2 of 1/2 is equal to negative 1. If you learn anything in this entire unit, I need you to be able to go back and forth between exponential and logarithmic form. That is going to be the answer to a lot of problems. It's going to help you solve so many things that this is the one thing I really need you to have. We're now going to practice solving some simple equations. So we're going to have some variables, and we want to solve for them to see what value we're going to get. First up, we have log base 8 of 64 equals n. I don't know that off the top of my head, but if I switch it to exponential form, I'll have 8 to the n power is equal to 64. So 8 to what power is 64? Well, that's the second power, so n equals 2. Next up, we're looking at log base 3 of z is equal to negative 1. If I put that in exponential form, I'll have 3 to the negative 1 is equal to z. That means z is equal to 3 to the negative 1, that's equal to 1/3. Next up, we have log base b of 16 is equal to 2. Converting that, we'll have b squared equals 16. If you take the square root of both sides, you get b equals plus or minus 4, so positive or negative. But we said that our base needs to be positive, so we're only going to take the positive answer, b equals 4. Next up, we have log base 2 of 1/8 is equal to c. So we'll have 2 to the c power is equal to 1/8. Well, I know that 2 to the third is equal to 8, but to put that 8 in the denominator, I need to make it an exponent of -3. I want c to be equal to -3. Finally, we're looking at log base 2 of the square root of 8 is equal to p. This one is tricky. Let's see what we can do. If 2 raised to the p power is equal to the square root of 8. Well, that one's a little bit different than what we've seen so far. So I'm going to do a little math-a-magic over here and see what we can do to figure this one out. We know that 8 is equal to 2 cubed. So that means the square root of 8 is equal to the square root of 2 cubed. If I put this into our fractional or rational exponent form, that will be 2 raised to the third power. That 3 is going to be over a denominator of 2 because it's a square root. So that means I can rewrite the square root of 8 as 2 to the 3/2 power. So I get 2 to the p is equal to 2 to the 3/2 power. Well, that means p equals 3/2. So sometimes you have to play around a little bit, see what you can find, use our exponent rules, and that'll help you simplify some stuff. This is kind of the basis of moving into logarithmic equations. So make sure you have this because they are this is the building blocks that we need to move forward. There are 2 buttons on your calculator that you need to become really familiar with. The first one is the common log button, and it's LOG on your calculator. So this first one, the common log, has a base of 10. So if you just see the word log, it means log base 10. That's what it stands for. So if you do not see a subscript, you don't see a base there, we know it's 10. If you use the log button on your calculator, the LOG, that's going to be log base 10. So with our calculator, we want to evaluate f of x equals log of x for x equals 4 and x equals 52. So they just want me to find the log of 4. I'm going to round to 4 decimal places. So the log of 4 is roughly equal to 0.6021. And the log of 52 is about equal to 1.7160. Common log is common. That's why we give it kind of this shortcut of not having a base. But it really does have a base. It's 10. We're just not writing it. There is another logarithm that we don't write the base for, and that one is our natural logarithm. The natural logarithm has a base of e. So that number e that we've been using, that can be the base of a logarithm as well. So the way we write natural logarithm is ln. So if you see ln, I typically write my lowercase l's as script l's, just so you know. That means log base e. Right, so the natural logarithm has a base of e. Natural logarithm is written as ln. Use your calculator to evaluate f of x equals natural log of x for x equals 2. So we need to find our ln button. Mine is right below logarithm. So the natural log of 2 is about equal to 0.6931. And the natural log of 0.3 is is about equal to a negative 1.2040. So natural log is going to be ln, common log is going to be log. Natural log has a base of e, common log has a base of 10. Those are going to be some key components that we have. Wait a minute, what if I need to calculate a logarithm whose base isn't 10 or e? I don't have a button on my calculator to do like log base 5 or log base 12. So how do we handle that? That's what the change of base of formula is for. To evaluate a logarithm that does not have a base of 10 or e, we're going to use the change of base formula. That says if we have log base a of x is equal to the log of x over the log of a, or the natural log of x over the natural log of a. You can use either one. So if we want to calculate log base 4 of 30, using this change of base formula, I can use the log of 30 over the log of 4. I could use the common log. Let's see what that gives me. The log of 30 divided by the log of 4. I'm getting 2.4534. But I could also use the natural log. If I do the natural log of 30 over the natural log of 4, notice I'm getting the same value. So it doesn't matter whether you use common log or natural log as long as you use the same one in the numerator and denominator. So for the change of base formula, you're going to do the log of the big part divided by the log of the base. We're going to talk about what that big part represents moving forward. So we need to talk about the domain of a logarithmic function. Before we were talking about logarithms, we were talking about exponential functions. Exponential functions had a domain of all real numbers, meaning you can plug in any x value. Logarithmic functions are not the same way. Logarithmic functions are more picky on their domain. You can't plug everything in. So we're going to consider the inverse relationship between logarithmic function and its exponential form. So these two mean the exact same thing. This x here, the thing that comes after the base, so this a is the base. This thing here, this x, it is called the argument. Well, that argument is the answer or the result of an exponential function. So think back to exponential functions. We want to know, can the argument of a logarithm ever be negative? When we were plugging into our exponential functions, did we ever get a negative out? No, because a was positive. And if you raise a positive number to a power, you're always going to get positive. So no, the argument can never be negative. Did we ever get 0 out? Can the argument of a logarithm be 0? Well, no to that either. We can get really, really close to 0, but we can't actually equal 0. So what we're saying is the argument cannot be 0, and it cannot be negative. So we want to know, what must the domain be? What values of x are allowed? Well, we can get really, really close to 0. So we use 0 with parentheses, and we can have all positive numbers. So the domain is going to be 0 to infinity. We can plug in any positive number as an argument. So what we're going to do next is we are going to look at the domain of these logarithmic functions in an algebraic fashion. Figure out algebraically, what are we allowed to plug into the logarithms? So we're going to find the domain of the following logarithmic functions. We have to keep in mind that the argument, which will be the thing in parentheses, has to be positive. So first up, we have log base 3 of 3x minus 1. We need the argument, the 3x minus 1. We need it to be positive. Think about how we say that mathematically. Greater than 0. I want to solve this for x. So I can add the 1 over, giving me 3x is greater than 1. If I divide by 3, I get x is greater than 1/3. So if I want to plug an x value into this logarithm, it has to be greater than 1/3. That's the inequality notation. If I want to put it in interval notation, that would be from 1/3 to positive infinity, because I want the x is greater than 1/3. Because it's just greater than, not greater than or equal to, I'm going to use parentheses. Next up, we're looking at the natural log of 5x. I don't care about anything except that argument if I'm trying to find the domain. I need that argument, 5x, to be greater than 0. If I divide both sides by 5, I get that x has to be greater than 0. So in that case, I'll have 0 to infinity. So any positive number can be plugged in. Next one's trying to be tricky. We're looking at the log of negative 3x minus 2. I still need that argument to be positive. So negative 3x minus 2 has to be greater than 0. We can add the 2 over, so we have negative 3x is greater than 2. To get the x alone, I divide both sides by negative 3. And you should have warning bells going off in your head. Something special is happening. We are dividing by a negative. What do we have to do if we multiply or divide both sides of an inequality by a negative number? We have to flip the inequality sign. It was greater than, now it needs to be less than. We get x is less than a negative 2/3. The way I write that in interval notation is negative infinity to negative 2/3. So be careful, if you multiply or divide by a negative on both sides of an inequality, that flip the sign is still in play, as it always has been. Finally, we're looking at the natural log of x plus 4. Just like always, I need that argument to be positive. So x plus 4 has to be greater than 0. If I subtract the 4, I get x is greater than negative 4. I would write that in interval notation as negative 4 to infinity. So I can plug in any number between negative 4 and infinity, and I'll get something out. Now that we know a little bit more about the domain of these logarithmic functions, we're going to try graphing one. I have told you time and time again, and I'm going to keep telling you, if we are graphing a function and you don't know how to graph it off the top of your head, make a t-chart. It's good for you. It's helpful. Life is good. Yay. So let's try it. I try to pick x's that go from negative 3 to positive 3. And then I just plug them in. So first up, I want to find log base 2 of negative 3. Well, this one's not a log base 10 or a log base e, so I'm going to have to use that change of base formula. So that will be the log of negative 3 divided by the log of 2. And I'm going to have to type that into my calculator. So I get the log of negative 3 divided by the log of 2. And my calculator is giving me an error, like I'm getting something wrong. Do you see the problem here? Think back to that last slide when we were talking about the domain of logarithms. We said that the argument, in this case is x, has to be positive. I'm trying to plug in a negative 3 as an argument. I can't. That's not allowed. So I don't get a y value when x is equal to negative 3. Well, I can't plug in negative 2 either because that's negative. I can't plug in negative 1 because that's negative. I wasn't allowed to plug in 0 either. I guess I can only do log base 2 of 1, 2, and 3. So let's try that. Log base 2 of 1, if I use the change of base formula, I can type it in as the log of 1 divided by the log of 2. That's equal to 0. If I plug in log base 2 of 2, that'll be the log of 2 divided by the log of 2. That's 1. And if I plug in 3, I'll get a value of 1.585. So let's plot the points that I can. I have 1, 0, that's here. I have 2, 1, that's here. I have 3, 1.58 stuff. So something like that. Is that enough to give you an idea of what this graph looks like? Because that doesn't really help me. So what can I do? I'm going to leave these points here because I know they are on my graph, but they're not enough to help me. I'm going to leave the points there. We're going to try looking at this a different way. We said that we can write our logarithmic equations in exponential form. If I write the logarithm on the left, log base 2 of x equals y, and I switch it to exponential form, I will have 2 raised to the y power is equal to x. If I can graph this equation, then I'll be graphing the same thing. Looking at this equation, is it going to be easier for me to pick x values and solve for y? Or is it going to be easier for me to pick y values and solve for x? I think it's going to be easier if I pick some y values and solve for x because I just have to take 2 raised to that power. Well, in exponential form, I can plug anything into an exponent. I can pick negative numbers, I can pick positive numbers, I can pick 0. So instead of picking values for x, I'm going to pick values for y. So we'll try y equals -3, -2, -1, 0, 1, 2, and 3, and see if that helps us any more. So this time I'm plugging in -3 for y. 2 to the -3rd power is 1/8. 2 to the -2 power is 1/4. 2 to the -1, 1/2. 2 to the 0, 1. 2 to the first, 2. 2 squared, 4. 2 cubed, 8. That gives me 7 points I can plot. So 1/8, -3. 1/4, -2. 1/2, -1. 1 0 is already on here, 2 1's already on here. 4, 2, and 8, 3. That gives me a lot better idea of what's going on here. It looks like I'm going to get really, really close to this y-axis. And then I have this kind of upward curve going on, something like that. That's way better than just picking x values and plugging them in, because I can plug in more things. So if you're graphing a logarithm, try putting it into exponential form, and then pick your y values and solve for x. We're going to look at some of the properties of this graph. I'm going to redraw it so that we can see it on this slide. So it was here, 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 here. Yes. So first up is the domain. Well, we were already finding the domain of logarithms before. We say that the argument, in this case x, has to be positive, meaning it's greater than 0. So we know x has to be greater than 0, which would be 0 to infinity. That matches up with our graph because we're never going to reach the y-axis. We're going to get really darn close. We're not going to touch it. The range is the y values that I'm going to hit on this graph. Well, this is going to keep going up. It's going to go up slowly, but it will keep going up forever. So I can get anywhere from negative infinity to positive infinity. Y-intercept is where we cross the y-axis, but we never touch the y-axis, so there isn't one. X-intercept, though, that's where we cross the x-axis. That happens at 1, 0. Horizontal asymptote is a horizontal line that we get really, really close to. This is going to keep going up forever. We're not going to flatten out. So there isn't a horizontal asymptote. Vertical asymptote, on the other hand, is going to be that vertical line that we get really close to. And that's going to be our y-axis. It's a vertical line, so if we think Vux Hoy, vertical lines have an undefined slope. Their equations are x equals. And we're getting really, really close to x equals 0. So you'll notice that the domain and range are flipped from what they were with exponential functions. And sort of the same idea for x and y intercepts, and sort of the same idea for vertical and horizontal asymptotes. That's kind of this idea that they're inverse functions. That's why this is all happening. We're going to bring back the idea of graphing with transformations as well, because we just want to discuss it. I'm not going to go into full detail with this, but we've been dealing with the graph y equals log base 2 of x. And that looked like this. If we want to add a 1 to the x, that means we're going to be moving in the x direction. And if we're moving in the x direction, everything's backwards of what you would think. So instead of moving in the positive 1x direction, we're going to go in the negative 1x direction. So if we add a 1 to the x, we're going to shift 1 to the left. We could take this entire graph, shift it to the left 1 unit. Similarly, if we subtract 3 from the x, you would think we're moving to the left, but because it's the x direction, it's opposite, so that would move us 3 to the right. If we're adding and subtracting to the back of the function, so not directly to the x, that's going to move us up and down, and that's going to be normal. So plus 2 on the end moves us up 2, minus 4 on the end moves us down 4. The negative symbol, if we have a negative attached to the x, then we're going to flip in the x direction, which means we're flipping across the y-axis. And if our negative isn't attached directly to the x, then I think of it as being attached to the y. So we flip in the y direction, which is across the x-axis. So keep these in mind, that this is a way that you can graph as opposed to making a t-chart for everything. It works, it's just a different way of thinking of it.